Thank you so much for listening to our presentation. My name is Patrick Guansen Tong. Today, I'll present you our work for submission to TVCG and HPVR, Multimodal Neuroacoustic Fields for Immersive Mixed Reality. Well, immersive audio rendering in 3D is crucial in AR/VR because it not only allows us to hear the experiences, but also match the visual environment. However, existing methods struggle with spatial realism and performance. The applications of an algorithm like this is in many folds. Imagine when you were hearing a music or ocean waves or an unique experience that is driven by audio, and now you are placed in a new environment. With this algorithm, you can re-experience the audio that you heard before and have that be as immersive as possible in the new space. Traditional methods in audio spatialization are very computationally intensive or specific to certain conditions. In the recent years, deep learning algorithms have been proposed, such as NAF or INRAS. They're usually more efficient and generalizable. They can synthesize audio at arbitrary emitter and listener position. However, they are not as generalizable across environments, but they require a 3D mesh, which is oftentimes very hard to obtain in the real life. We take this problem from another angle. We're given a visual acoustic input from source and pulse of target viewpoint. We synthesize the audio at the novel viewpoint. The first work to tackle this problem was solved by Zheng et al. 2022. However, they neglect complex relationships between visual audio and coordinate inputs, and they lack conventional results in realistic scenarios with noise. We aim to improve upon these limitations. Here is the model overview. We first take in a source viewpoint and a RGB or depth if available, and we pass that into a conformer or transformer augmented with convolutional layers. In this step, we aim to learn the visual acoustic correspondence before we pass this into an audio decoder inspired by WaveNet, where we take in the speaker and listener positions, and we seek to learn the primary audio effects driven by first-order reflections and direct sound emissions. And at last, we synthesize the non-seen audio at the novel position. The visual acoustic correspondence is primarily handled by a conformer, and most importantly, it is handled by the cross-modal encoder attention layer, where we calculate the attention score between each patch of the visual scene and each sequence of the audio. To model waveforms, we take inspirations from the previous work in WaveNet, which is exceptionally good at capture long-distance dependencies, and we augment that architecture with dilated convolutions with learned spacings, where we give the grids between the kernel positions as an additional learning parameter, so that we can learn spaces between the grids more effectively, which allows us to extract more fine-grained details. For the loss function, the first loss term will be a loss term that is the summation of the summation loss and difference loss, where the summation ensures that overall content among the left and right channels is preserved, and the difference loss prevents the network from blending the two channels aggressively. Another loss term is the multi-resolution loss, which captures both coarse and fine spectral features in the Fourier domain. And the final loss is the summation of the multi-resolution loss and the stereo loss.
Use a benchmark dataset for our evaluation. This consisted of sound spaces, which involve audio synthesized in simulated environments. We also use the replay dataset, which involve recorded 5-minute conversations from 8 viewpoints in the real environment. We get 1-second samples from the datasets. We also created our own dataset called M-Sound. This was recorded using 2 iPhone 14s. It spans 7 environments, and it includes different room sizes, lighting conditions, and visual clutter. The audio within the dataset is diverse, as it involves varied scenarios like conversations and monologues. And it also includes noise ranging from quiet offices to busy restaurants. We first evaluated our model by comparing our model against Chen et al. 2022 and multiple other baselines. Our method outperforms the other baselines on all datasets. On M-Sound, it outperforms by 18% on the magnitude error and 11.6% on the RT60 error. On the replay dataset, it outperforms by 29.9% on the left-right ratio error. Now we will demonstrate comparisons.
Hey, what's up? How do you like this place?
I think it's pretty good. What kind of food do you like here?
Well, I'm here for the coffee. I love espresso. Hey, what's up? How do you like this place?
I think it's pretty good. What kind of food do you like here?
Well, I'm here for the coffee. I love espresso. Hey, what's up? How do you like this place?
I think it's pretty good. What kind of food do you like here?
Well, I'm here for the coffee. I love espresso.
I went to high school in Hawaii, and I stayed in Honolulu for 3 years. I think that's a very special experience. I went to high school in Hawaii, and I stayed in Honolulu for 3 years. I think that's a very special experience. I went to high school in Hawaii, and I stayed in Honolulu for 3 years. I think that's a very special experience.
Now we'll go on to our perceptual studies. We had 12 subjects and 11 scenes, and the task was firstly to memorize 11 reference audios and 33 randomized trials. And so for each scene, the user was asked to listen to 15-second stimuli in VR from one of 3 methods, either our method, Vigus, or the reference. This was randomly ordered. The participants were asked to identify if the audio matched the reference. And we showed that there was a significant difference between the perceived sound quality for our method and the other method. The baseline, the other model, was worse than our method, and there was no difference between our model and the reference. We also used an AR/VR application where we recruited 6 participants who were asked to judge immersiveness. In the VR experiment, they were asked to walk through a reference concert with original audio. Afterwards, they walked through a virtual environment with immersive audio. This was repeated once with our audio and then the generated baseline. The AI experiment was as follows. The user was asked to listen to music from virtual speakers, and this was repeated once for our audio and the baseline. In summary, ours outperformed Vigus on several metrics in both the AR and VR study.